Namaste. Welcome to tutorial series on SuperPro Designer for beginners, a step-by-step guide to process simulation. In this tutorial, let us understand how to simulate a batch enzymatic kinetic reaction. This example file which I am showing here, which is shipped along with the SuperPro Designer trial version. For your information, I am using version 13 of SuperPro Designer and build 2. This example file is not available with build 1. So those who are using build 1, please download the latest version of the software and you can access this particular file. So in this, the enzyme reaction, that is sucrose hydrolysis to glucose and fructose, is simulated. Why this particular example is interesting and important? Because as such in SuperPro Designer, there is no operation to simulate the enzyme kinetics. So the available operation needs to be used to simulate this particular case. In this case, the ferment kinetic operation is employed to simulate the enzyme kinetics. Let us see how to utilize that particular operation and simulate the enzyme kinetics using the given data for enzyme reaction. To access the file which I showed right now, you can go to the process library, which is having a lot of examples shipped along with the software. You can notice each folder is having multiple files cater the needs of different industries. Under this examples file, there is a folder called miscellaneous. Under this miscellaneous folders, there are a lot of simple examples available which help us to understand and learn some advanced features in the SuperPro Designer. For this tutorial, I have chosen this enzymatic kinetic reaction, and also along with this there is one more readme file is available which clearly give the information on this particular process simulation. This is the word file which clearly gives the step-by-step instructions, and also it is clearly defined here how to set up the kinetics, enzyme kinetics, using that particular available ferment operation, and also the details are given. So what is the rate of sucrose is added and how much enzyme is added, what is the km value, that is the macalisme constant value, Vmax value. All this information is also given, and also they have assumed some values, and also clear details are given here how to kind of convert those given values to the required values. And also at the end they generated the dynamic data records using the profile option, as well as creating an Excel file that is the time versus concentration data, and also it is plotted using the Excel, and it is again imported back to the SuperPro Designer to monitor this concentrations versus time data. So let us start the simulation, and I will explain step by step how to use this particular ferment operation or ferment kinetic operation to stimulate enzyme kinetics. I have just taken extracted data from that readme file which is available in the process library folder, and also here some conversion is factors are given. Let us see what is this values Vmax and Km. For your information, I am using the batch mode operation. That is, mode of operation is in the batch mode, and it states that sucrose, that is 5% sucrose solution, is used in a reactor, and the reaction is carried out at 55 degrees centigrade, and all the enzyme is added at a concentration of 5 mg per liter. This is the concentration which is used in this particular process, and yeah, the specific activity of enzyme is assumed as 400 units per mg, 400 units per mg. But in the SuperPro Designer, when you see the values that need to be input, that is basically in gram per liter per hour or per hour, because basically in monad kinetics the mu which is used in per hour basis, and the same of this particular units per liter I cannot feed into the software. That is the reason it is converted into gram per liter per hour. And also the Km which is a macalisme constant. In case of monad kinetics, it will be Ks, that is again mg per liter. The unit available is mg per liter, so we need to convert the whatever the value of Km is given to mg per liter. So I'll just show you the interface of that ferment kinetic operation so that you can understand better. This is the interface of fermentation kinetics, the dialog box which we see. In previous videos also, we use this particular dialog box to simulate some fermentation kinetics. So if you could notice here, the monad kinetics is mu is equal to mu max into S divided by Ks plus S. And the Michaelis Menten kinetics also, it is in the similar lines that but we define this velocity V is equal to V max into S divided by Km plus S. So in this particular dialog box, you can notice that, so almost it is closely resembles to the Michaelis Menten one. You can notice there S1 term is there, S2 term is there, S3 term is there. But here we have only one substrate, that is sucrose, and also here there are no inhibitors or like other components. That is the reason our dual substrates are available. You go with S1 term for one substrate, S2 term for other substrate. Maybe you can use S3 term for inhibitors if any inhibitors are available to define. For example, if I choose this particular inhibitor S3 term, and I can go with inhibition. So I can choose this inhibition, and what is the inhibitory constant, all these things you can define it. But in this case, it's a simple enzymatic reaction, so I just go with S1 term. And if you see the rate equation, which is an inbuilt equation, the unit is gram per liter per hour, gram per liter per hour. And if you could notice, there is an alpha, mu max. In our case, it becomes V max. And S1 term, what is the S1 term? S divided by Ks plus S, means it takes care of this one, that is S Km plus S. And we will neglect this S2 term, S3 term, and also the beta term also we neglect it, because that will be in term when we go with microbial kinetics, this beta terms comes into the picture. But now we will just neglect this beta term. And also B term, if there are any biomass in the system, that the B term should be considered. But in this case, there is no biomass also, we can neglect this B term also. So now if you neglect this B term, beta, S3, S2, we just ended up with alpha mu max into S1 term. Now in this case, alpha is also 1. So then it becomes simple Michaelis-Menten kinetics model. So you can just substitute this particular V max here, so that, and also you can notice the Ks. Now in this is Km, that is mg per liter. So whatever the Km which is given in millimolar, that need to be converted into mg per liter. Let us see the further when we set up the whole process, we can understand better. Just now we understood the fermentation kinetics dialog box there. The Vmax is in terms of gram per liter per hour. So the 2000 units per liter, because the concentration of 5 mg per liter and enzyme which is having 400 units per mg, when you multiply these two, you are going to get 2000 units per liter. Now this 2000 units per liter need to be converted into gram per liter per hour. And also here one more hint is given, that is one activity unit is defined as amount of enzyme that converts 1 micromole per minute of substrate. Here in this case, substrate is sucrose. So according to definition, that is 2000 units per liter. So each unit is nothing but 1 micromole per minute, 1 micromole per minute. This unit you get cancelled. And next one, the micromole is converted into mole. So we know 1 micromole is nothing but 10 raised to minus 6 mole. And further the mole is converted into gram, that is 342 gram, that is based on molecular weight of sucrose, it becomes 342 gram, 1 mole is 342 gram. And next one, we need it in hour, because the unit is like a micromole per minute, so we need to convert the minute to hour. So 1 hour is 60 minutes, a simple conversion which leads to the value of 41.04 gram per liter per hour. And also here it is assumed that Km is 30 millimolar. So, but we need to input the value in terms of mg per liter. So 30 millimole, as per the definition of molarity, we can write it as millimole per liter. And 1 millimole is nothing but 342 milligram of that particular sucrose. And when you do the calculation, it becomes 10260 mg per liter. I hope you understood how to calculate this Vmax and Km from particular given data. Let us start the simulation. First very important thing is we need to register the pure components required for the simulation. Let us go to this task, pure components, and as such there are no stock mixtures are required, all are pure components. Let us go and register. Sucrose is the important ingredient. Sucrose, it's already available in the database we selected, and once the sucrose is hydrolyzed with water, we are going to get glucose and fructose. So water is already available, we no need to register that one. Glucose is again widely used chemical in bioprocess industry, so it is already available in the database, we will add it. Fructose and invertase, the enzymes are not available. Let us go and register it as a new component. Yes, we can register fructose with instead of registering with the pure properties of water, I can register with glucose, because both the fructose and glucose are isomers, so most of the properties are similar, so I'll register with glucose properties. And also we need to register one more component, that is enzyme. Will invertase, that is an enzyme. And you can either register with the properties of water, or there is proteins are also available. Proteins are also available, you can register along with the protein properties. Click OK. And one more thing, according to the flow sheet, which is the example flow sheet, the molecular weight taken is 60,000 gram per mole. 60,000 gram per mole. Click OK. So all the required ingredients we have registered. Click OK. Next, we need to add the procedure. Here in this case, a simple reactor is used. We no need to have a bioreactor. Simple reactor is sufficient to simulate it. And we need to add the input and output. We need one stream for sucrose and another stream for enzyme. And also we can connect it to vent, and the output is the product. So let us rename this particular stream as sucrose, that is 5% sucrose, and we can add, or we can rename it as enzyme. So next, this is the product stream. This is the product stream. This is the product stream, and we can rename this as vent. Rename this as vent. So click OK. So we already added all the streams. Now the operations, what are the operations required for this simulation? We need, as it is a batch process, we need to add the operation. First very important operation is required, that is charge. We need to charge the sucrose. That in this problem 1000 liter of 5% sucrose solution is charged. We need a charge. And also the problem statement says that the concentration of enzyme required is 5 mg per liter. And also you can do a easy back calculation. For 1000 liter, per liter it is 5 mg, 1000 liter it is become 5000 mg or 5 gram per liter. But SuperPro has an option, because it is a simple problem, a simple case, so you can easily calculate, and you can even charge the enzyme based on the calculation. But we have a wonderful option called as pull-in operation. This pull-in operation will help me to calculate the quantity of enzyme required based on the criteria. That is the reason we can use this pull-in operation. And before pull-in that particular enzyme, we need to heat the sucrose solution. So let us add heat operation before the pull-in operation. Please carefully understand. First we charge it, then we heat the mixture to 55 degrees centigrade, then we pull in the enzyme to the reaction mixture, then we need to carry out the reaction using ferment kinetic operation. So why do we need to use ferment kinetic? Why not stoichiometry? Because the kinetic information is given here. Let us go with ferment kinetic, add it after like pull in. And the last operation generally is transfer out operation. So you can even rename this one, that is charge 5% sucrose, 5% sucrose, and this you can rename it as heat or heat to reaction temperature, and you can rename it as add enzyme, and you can rename this as enzymatic reaction, and this one you can rename it as remove contents. So these are all the operations. Click OK. And we need to initiate this particular streams. Let us go to this sucrose stream, and we initiate this one. So sucrose is the required, water is required, and total quantity is based on volume, that is 1000 liter per batch. and sucrose is 5%, water is 95%. So click OK. Click OK. Next, let us charge the enzyme. So let us click this particular dialog box. We can charge this invertase here, and also as I already told you, we can calculate it, back calculate it, 5 mg per liter for 1000 liter, how much it is. You can back calculate and charge the enzyme also. But in this case, we are using an advanced option called as pull in. So let us go with auto adjust. So based on the criteria what we set later, so automatically this quantity will be calculated. Click OK. Next one, let us initiate the operation. Let us go and charge the sucrose, charge here. So what is the sucrose string? That is sucrose 5%. How much I already initiated in the user amount on the stream. Let us go with this. And also the process time and setup time. Simple process time of 30 minutes we will set it, and we will go with setup time of 0 minute. So this is what a simple initiation. We go to the next operation. The next operation is pull in operation, heat operation. That is, we need to heat it to 55 degrees centigrade using steam, and rest all we go with the default value, and click next. And next is pull in operation. That is, we need to pull the enzyme. How much? So based upon some criteria, that is, we go to advanced option, set final concentration. For invertase, the concentration is first let us choose the mg per liter, that is 5 mg per liter. Automatically the software will calculate the required quantity. Click OK. And also we can have simple the setup time of 0, process time of 5 minutes, and rest all we go with the default values. Click next. Next very important thing is the enzymatic reaction. So here the enzyme reaction is carried out 55 degrees centigrade. If any heat is generated, that need to be cooled using cooling water, and the reaction is carried out for 2 hours. So next one, volumes, fed batch, all this we go with default value. It is not a fed batch process. So next very important thing is reaction. So let us set up the reaction stoichiometry. According to the problem statement, it is sucrose reacts with water in the presence of enzyme invertase, gives glucose and fructose. So let us select the molar, even in the mass basis also, because all the molecular weights are correct, whichever we have added. So that is the reason you can notice 360, or else you can choose the molar also. You can notice 1 mole of sucrose plus 1 mole of water gives 1 mole of glucose plus 1 mole of fructose. Click OK. And we need to set up the reaction stoichiometry. This is very important. Please understand carefully. I've already explained in the introduction how to utilize this dialog box. Now, in this case, the substrate is sucrose. And also the rate reference component. We are trying to work with respect to the reference component of sucrose. And also, just now we calculated here, that is Ks we have calculated. So what is the value of Ks? That is 1. Ks is nothing but Km here. 10260 mg per liter, and also the Vmax whatever we calculated, that is 41.04. These things we have calculated. And one more thing you should not forget, B term. There is no B term. B term is not required, so we have to choose the none. So rest all we go with the default value. Now as of now, alpha is 1, so it is neglected, and mu max is nothing but Vmax. And S1 term, that S divided by Ks plus is nothing but Km plus S. So Ks is added here. So click OK. So now we need to add the heat of reaction is given. Heat of reaction is kilojoule per kg. So let us choose kilojoule per kg. It is nothing but minus 78.9 with respect to sucrose, and 25. Reference temperature is 25 degree centigrade. So we added all the information. Let us see, based upon this criteria, what is the percentage of conversion that we could able to achieve it. Next very important thing is, whenever we want time versus concentration data, so that need to be chosen in profile. So I need to understand that how this particular sucrose is getting depleted, and also the glucose is getting formed in the process. So in the number of points, data points required with respect to time is 21. We are going to get 21 points of data. If you want more data, you can do it. As these differential equations are solved, so automatically this data will be generated. So next, the profiles, rest all we go with the default value. Click next. The last operation is transfer out operation. So that is product, and we are transferring it out 100%, and you can have some setup time of 0 and a process time of 30 minutes. So as per the data given, we have added all the information to the streams as well as operations. Let us simulate and check are we correct. So it is saying that, so stream port 12, that is in P1 R01 in enzymatic batch kinetics, is currently missing. So this is here. We go back to operation and reaction, and sorry, the next operation, heating, pull-in operation, and the next operation is yes, this one. Here it is showing the port 12. The port 12 is missing. That's what we have not unchecked it. I have also done a mistake. So we need, even though we connect it to other stream, we have to just unselect this one. So click OK and let us try to resolve. So yes, there are no errors. Errors have been resolved. So next, if you could open this product stream, you can understand sucrose still, that is 1.98 kg per batch of sucrose is left out, and equal quantity of fructose and glucose is formed, that is 25.58 kg of fructose and 25.58 kg of glucose is formed. And how much the quantity of enzyme is drawn, you can notice here, approximately, if you take it in grams, it is almost 5 or approximately 5 gram per batch of enzyme is utilized. And also, if you want to know what is the reaction conversion, we can go back here to this reaction operation, and you can notice here, based on the criteria, and also for 2 hours, 96.08% that is of that particular sucrose got converted. If you want to further increase the percentage of conversion, you can have it for more time. Now, as per the criteria, it is conversion is 96.08. Click OK. Next one, very important thing is we need to understand time versus concentration data. For that, let us go to this dynamic data records and enzymatic reaction, and we need to link it to an Excel. So for that purpose, wherever you save this particular file, under the same folder, let us go and create an Excel sheet. Go and new. I'll create one Excel sheet here, Microsoft Excel. I'll rename with same enzyme kinetics.xls. So now let us go back to the software, and when you right click on this dynamic data records, first we should not forget to save the file, otherwise it shows an error. So let us go and dynamic data record enzyme kinetics, and here there is option to link Excel. So just edit it. When you click on this, automatically a dialog box opens and expect us to select the file. So here in this case, I will choose, because I have already chosen in the same folder. Excel is directly, SuperPro is directly recognizing. So I'll just select enzyme kinetics, click OK. Means whatever this time versus concentration data is there, that will be exported to this particular Excel sheet. So rest all we go with the default selections, auto update values. Any changes happens in this particular simulation file, automatically it will reflect in the Excel sheet. Click OK. So let us again simulate this. Excel sheet will be empty. Let us again simulate it and go back to this Excel file. And open it. Yes, you can notice here time versus glucose and sucrose values are available with respect to time. We have chosen 21 data points. So that is the reason, starting it from 0 to the end, that is 2 hours, it is divided into 21 data points. So we can plot the graph. You can choose this particular data, go to insert, and you can select, you can choose a line diagram. You can notice here, and you can even edit this one, add the chart title, all these things could be added here. So series 1, series 2, you can right click, select data, and you can add the series 1, you can edit it as glucose, and series 2 as sucrose, and also you can edit this axis. To add the axis, you can go to this chart design, chart element, axis, primary axis. Let us add the time, which is in hour, and next one, let us add one more chart element, that is horizontal vertical axis, that is concentration concentration, that is gram per liter. So you can edit this all the graphs, that is you can make it bold, you can edit this all the data points. So let us go with default values. Now I need to, you can also edit this title, enzyme reaction. So now we need to import this particular graph to SuperPro Designer. I'll just copy this one, select this and copy this graph, and let us go back to SuperPro Designer, and here under edit, so there is a paste special option, and link, paste the link Excel chart, because I already copied, so when I click it, it's already showing. Click OK. So yes, you can see here this particular graph is displaying here. So any changes you can do in the React. For example, you want 2 hours to 1 hour, you can change it. Concentration, you can change it. The value of Ks, Vmax, many values are available which could be changed, and you can easily understand how the dynamics of the overall process. In this, we are not bothered about scheduling, Gantt chart, all this thing, because we need to understand the simple batch enzymatic kinetic reaction. When you deal with any of this process or the enzyme reaction, or whenever you want to simulate a techno or perform some techno-economic evaluation of these enzymatic reactions, definitely this tutorial will be very useful. One more important doubt that people can get is like Vmax, here the unit is gram per liter per hour, but when we go to this enzymatic reaction, that is what the batch kinetic reaction which we chosen, and go to reactions, and this R symbol, when you go here, you can notice this mu max is per hour, but whatever we fed, this value is 41.04 gram per liter per hour. How it is correct? So because you can notice here, when the mu max is per hour, there is a B term, that is what you call it as biomass term is there. This biomass term could be gram per liter. So gram per liter into this per hour becomes gram per liter per hour. But in our case, so this is directly we have neglected this B term, and also this particular beta is neglected. So the mu max or V max, whatever we are inputting, the must be gram per liter per hour. Otherwise, this rate cannot be in gram per liter per hour, because the S is in mg per liter, and Ks is mg per liter, S is mg per liter. So this unit get cancelled. Ultimately ended up with we just having Vmax. The Vmax should be gram per liter per hour, and then the rate becomes gram per liter per hour. The unit consistency will be there. Otherwise, we don't get the unit consistency. I hope you understand this particular concept. So many people have a doubt that why the mu max here given is per hour, we fed the data with gram per liter per hour. Thank you for watching. Please do not forget to subscribe.